Welcome to this lecture on discrete mathematics. Today, we are going to explore a fascinating and powerful concept known as the duality principle. Imagine looking at a landscape reflected in a perfectly still lake. Everything is flipped, yet the overall structure remains exactly the same. We will see how this mirror effect applies to mathematical structures, allowing us to double our knowledge without doing any extra work. Let us dive in. Now that we have introduced the idea of a mathematical mirror, let us understand what the duality principle actually means. In the real world, a mountain peaks upwards and a valley dips downwards. In a reflection, the mountain points down and the valley points up. Everything is flipped, but the rules connecting the points remain identical. In discrete mathematics, the duality principle tells us that for certain structures, if a statement is true, its upside down version is automatically true as well. This matters because it saves us an enormous amount of time. Every time you prove one theorem, you get a second theorem completely for free. Building on this idea of a mirror world, let us look at where this principle is applied. We often work with a partially ordered set, or poset, which is simply a collection of items with a rule stating which item comes before another. To find the dual of any statement in a poset, you systematically swap every symbol with its exact opposite. Specifically, you replace the less than or equal to symbol with the greater than or equal to symbol. If you're working with lattices, which have unique upper and lower boundaries, you also swap the operations. You swap the join operation, which combines things upwards, with the meet operation, which combines things downwards. Before we apply duality to complex problems, let us see how it works on the foundational rules of ordering. A mathematical relation must satisfy three specific rules to be a valid partial order. The first is reflexivity. Conceptually, this means everything is related to itself. The formula is simply x is less than or equal to x. Here, x represents any element in our set, and the symbol represents the less than or equal to relation. If the value of x changes, the relationship still holds because an item is always identical to itself. Let us see what happens when we apply our mirror to this foundational rule. Now that we have our first rule, let us prove that its dual is also valid. This step is setting out to establish that the mirror version of reflexivity holds true. We start with our original statement. The mathematical reasoning here is simple. We apply the duality transformation by flipping the less than or equal to symbol directly to the greater than or equal to symbol. The intuition behind why this works is that equality is perfectly symmetrical. Saying x is greater than or equal to x is still a perfectly true statement. This proves that the rule of reflexivity works flawlessly in the mirror world. This brings us to the second foundational rule. Moving to the next building block, we have the rule of anti-symmetry. Conceptually, this rule states that if a first item is below a second item and the second item is also below the first item, they must actually be the exact same item. In our formula, we use logical symbols instead of English words. The upward pointing wedge is the logical AND operator, and the double arrow is the implies operator. If x and y were different numbers, they could not possibly be less than each other at the same time. Let us now find the dual of this logical statement. Let us derive the dual for this second rule. We are establishing that anti-symmetry is preserved under duality. The mathematical reasoning requires us to target only the inequality symbols in the premise. We flip both of the less than or equal to symbols to greater than or equal to symbols. Notice that we do not change the logical AND, the implies arrow, or the equal sign. The intuition here is that equality means the items are identical. So this flipped logic holds up perfectly in reverse. If x is greater than y and y is greater than x, they must still be the same item. This connects us to our final foundational rule. Our final foundational rule is transitivity, Conceptually, this acts as a chain connecting multiple items. If a first item is below a second and the second is below a third, the first must be below the third. Looking at the formula, we see three elements x, y, and z. The logical AND connects the two conditions, which implies the final relationship. If you increase the distance between x and z by adding more elements in between, this chain rule still holds across the entire set. Now, let us complete our proof of the axioms by dualizing this chain rule. To finish our derivation of the foundational rules, we will dualize the chain rule of transitivity. We are setting out to show that hierarchical chains work upside down as well. The mathematical reasoning is straightforward. We locate all three inequality symbols in the formula and reverse their direction. The intuition behind why this works is that if you flip a ladder upside down, the rungs are still in sequential order, just in the opposite direction. Because all three foundational rules remain completely true when we flip the direction, any complex theorem built from them will also remain true. Let us visualize this structural flip. Here we can visually see everything we just proved using a Hasse diagram, which is a drawing used to show the hierarchy of an ordered set. On the left, you are looking at the primal lattice. Notice how the structure flows upwards from the bottom element 0 through elements A and B up to the top element 1. Now look at the right side. The dual lattice is simply the original drawing turned completely upside down. The element 1 is now at the bottom and 0 is at the top. What this diagram teaches us is that the connections between the elements remain perfectly intact. The structural integrity is preserved even when the rules are reversed. Now that we have seen the visual proof, let us apply this to a specific mathematical statement. This formula defines a bottom element in a partially ordered set. Conceptually, it means there is an item smaller than everything else. In the formula, A represents this specific bottom element, and X represents any other element in the entire set. If the set grows larger, A remains at the very bottom of the hierarchy. We want to find the dual of this statement to see what the mirror image of a bottom element looks like. Let us work through this example. In this example, we are given the condition for a bottom element and we are asked to find its dual. We choose the duality transformation approach because it guarantees an equivalent theorem. The reasoning behind our first step is to isolate the relationship between the variables without changing their positions or names. We then replace the less than or equal to symbol with the greater than or equal to symbol. The physical meaning of this final answer is profound. While the original statement said there is a bottom element, the new dual statement says there is a top element. We get this second truth completely for free. Let us look at a slightly more complex formula from lattice theory, called the absorption law. Conceptually, this rule is used to simplify complex expressions. It tells us that if you combine an element upwards with a downward combination, the result collapses back down. In the formula, the V-shaped symbol is the join operation and the wedge shape is the meet operation. If you change the value of y, it does not matter because the variable y is completely absorbed and disappears from the final result, leaving only x. Let us see how to dualize an equation with multiple operations. For our second example, we are asked to find the dual of the absorption law. We use the lattice duality rules here, which require us to swap operations rather than just inequalities. The reasoning behind our steps is systematic replacement. First, we carefully replace the upward-pointing join symbol outside the parentheses with the downward-pointing meet symbol. Next, we replace the meet symbol inside the parentheses with the join symbol. The variables and the equal sign remain exactly as they were. The physical meaning of this final answer is that we have instantly generated a second mathematically true absorption law without needing to prove it from scratch. Now that we have used these formulas, let us understand why this matters in the real world. The duality principle is a massive time saver in computer science, specifically in digital logic design, which powers every computer and smartphone. Engineers use a specific version of this, called De Morgan's laws, to simplify complex circuits. By converting circuits built with AND gates into circuits built with OR gates, they can drastically reduce the cost of manufacturing microchips. If an engineer finds a way to optimize a circuit that detects when a signal is high, Duality immediately gives them the blueprint for a circuit that optimizes when a signal is low. It literally cuts their workload in half. To wrap up our lecture, let us review the key takeaways. First, the duality principle acts as a mathematical mirror for ordered sets and logic systems, preserving structural integrity even when flipped upside down. Second, by systematically swapping every relation and operation with its exact opposite, you create a dual statement that is guaranteed to be true if the original is true. Finally, this elegant symmetry is incredibly powerful because it halves the effort required to prove theorems and design logical circuits. You have now covered the full topic of the duality principle and are ready to apply these mirror rules to any discrete mathematics problem.